Good afternoon, everyone, and welcome to our live seminar series. My name is Olivia Lanes from IBM Quantum, and I'm very excited to be able to host the seminar today and to introduce today's speaker, Professor Robert McDermott from Wisconsin. So I'm just going to give everybody a few minutes to tune in here and go ahead and tell me where you're tuning in from today. I am from my apartment, still remote, in New York. Hey, Kyle. Nice to see you. Just give everyone a few minutes here to tune in. Have some people tuning in from Danbury, Connecticut. That's not too far. Rutgers, New Jersey, Amsterdam. Okay, that is the farthest so far. Mumbai, London. Give everyone just a few more minutes. Okay, awesome. I think we are just about ready to get started. So good afternoon again. Hi, everyone, and welcome to our live seminar series. My name is Olivia Lanes from IBM Quantum, and I am very excited to be able to be here to host the seminar series and to introduce today's speaker. We are thrilled to roll out the latest episode of the Qiskit Seminar Series, which is dedicated to the research and academic quantum communities. The seminar series will take place every Friday at noon Eastern Time and is hosted on our Qiskit YouTube channel. I'm your host for today. Hi, Olivia again, and I'm very excited to be here speaking with Robert McDermott. So I'll just go ahead and introduce Robert, and then we'll pull up his slides. Feel free to ask questions throughout, and we'll get started. So Professor Robert McDermott received his Ph.D. in the group of John Clark at UC Berkeley in 2002. Following a postdoc at NIST Boulder and UC Santa Barbara in the group of John Martinez, he joined the University of Wisconsin-Madison in 2006, where he is a professor of physics. He leads an experimental superconducting quantum computing group that is focused on the development of tools to enable the continued scaling of superconducting qubits towards fault tolerance. Separate research directions include scalable qubit control and measurement, fundamental studies of decoherence, development of novel protected qubits, and quantum sensing for dark matter detection. Robert, thank you so much for being here today. How's it going?
It's going well. It's going well. Thanks for that. Thanks for that introduction. So I'm calling in from my house in Madison, Wisconsin. I look forward to be getting back into the lab next week now that I'm fully vaccinated. Anyway.
Yeah, we were talking about that earlier. That's super exciting. Yeah, so this is great. I think we're ready to pull up these slides and get started. Just as a final reminder, feel free to ask questions throughout. I'll be monitoring the chat, and I'll do my very best to politely interrupt you if there are any questions, and we'll just let you take it from here.
Okay, sounds good. Well, today I'll be talking about some recent experiments that we've done in my superconducting qubit lab at UW-Madison to understand correlation of errors in multi-qubit circuits. This is work that we've done under a grant from Department of Energy. I want to acknowledge their support. Okay, so here's an outline for my talk. I'll begin with a brief overview of the demands for performing full error correction in a large-scale quantum computer. Talk about why that's challenging and why correlated errors in particular are quite damaging. And then I'll get into our experimental results from UW-Madison. I'll begin with a brief overview of what we've found over the last several years in our studies of charge noise in superconducting qubits. This is actually how we came to think about the possibility of correlated errors in superconducting qubit arrays. And then I'll get into the heart of the talk. And there are two pieces here that are described in this paper that's posted to the archive from December of last year. What we find is that high energy particle impacts on the superconducting qubit chip give rise to correlated errors. And there are a couple of different pieces to this physics. I'll talk about the charging event associated with these impacts and how that can couple to multiple qubits. But a more damaging piece is correlated relaxation errors due to phonon-mediated quasiparticle poisoning. So I'll spend some time talking about the physics there. In the last part of my talk, I want to shift gears a little bit and talk about um, some different physics associated with quasiparticle poisoning and some new thinking there that we've described in this other paper that was posted to the archive last month. And then I'll conclude. Okay, let's go ahead and get started. So it's incredibly challenging to build a quantum computer, and part of the complication is that quantum states are incredibly fragile, and even weak coupling to the environment can destroy some delicate entangled quantum state. But a big part of the problem is that errors in a quantum system are much more subtle than errors in a classical computer. So classically, if you've got a bit, there's only one thing that can go wrong. The bit can flip. 0 can go to 1 and 1 can go to 0. Well, in the quantum world, you can have superposition states that are, you know, kind of admixtures of 0 and 1 with different amplitudes and different quantum phase. And so in addition to having the usual bit flip error where the excited state relaxes down to the ground state, or the ground state gets excited up to the 1 state, you can also have a phase flip error that flips the phase of a superposition state. And you might naively think that, okay, we can monitor and correct both types of errors by just probing the system and looking for bit flips and phase flips repeatedly. But you can't do this in the quantum world because the operators that correspond to bit flips and phase flips, they don't commute. And so monitoring and tracking errors in a quantum circuit is a very difficult, subtle business. Now, the good news is that very bright people have showed that by encoding quantum information in a larger array of interacting entangled qubits, that it is in principle possible to uniquely identify and track errors in the quantum system, provided that operations on the array are performed above a certain threshold level of fidelity. So that's a very exciting result. And this underpins a lot of the optimism for possibly realizing a quantum computer using systems like superconducting integrated circuits. And one of the developments of the last decade or so is that groups like IBM and others are now able to operate superconducting qubits at a level of fidelity that is, at least in principle, compatible with fault tolerance. And the architecture that a lot of people are thinking about for fault-tolerant quantum computing is the so-called two-dimensional surface code. And I show a little cartoon here from a nice paper from the UCSB group from 2012. And so there's this worldwide push to implement a fully error-corrected quantum computer using this approach. Now, while the levels of fidelity have been obtained in kind of smaller scale, let's call them demonstration experiments, it does remain incredibly challenging to retain those levels of fidelity as systems are scaled to larger and larger sizes, as would be needed to implement a full-blown, fully error-corrected quantum computer. But another important piece of this surface code business is that the scheme for monitoring and correcting errors relies on the assumption that errors in the array are not correlated. So if you've got errors that are correlated either in space or time across the array, then this whole analysis kind of falls apart. So it's very important for us as a community to understand whether there are correlations in the errors that superconducting qubits are subjected to? And if so, we need to really understand the physics and develop appropriate mitigation strategies. So this is what my group set out to do a year or so ago, to really characterize correlations of errors in superconducting qubit systems. And I want to begin with maybe like a little bit of a historical background so that people can understand why we came to be thinking about this problem. So this effort grew out of a long-standing project in my group to understand the uh, fundamental physics that governs decoherence in superconducting qubit arrays. So we're looking at flux noise, we're looking at quasiparticle poisoning, but another piece of this is charge noise. And so we had a project to understand the frequency dependence of charge noise, the scaling of charge noise with device scale. And the test bed for these projects was the weakly charge sensitive transmon qubit. So here you've got a superconducting island that's shown in magenta here, that's embedded in a superconducting ground plane with a little bit of a gap. So that island forms a qubit capacitance, and that capacitor pad is connected to ground via Josephson junction, which you can't really see in this optical micrograph. And the length scale here, this island inner radius is about 70 microns. So for experts, we've got a qubit, transmon qubit, that's not quite in the transmon regime. So we've got a ratio of Josephson energy to charging energy of this island that's about 25, which means that the device has energy bands that tune with offset charge or tune with applied electric field to the island. And so, for the purposes of understanding the experiments that I'm going to describe today, it's useful to think about the qubit as an electrometer, an electric field detector with a large effective sensing area that's allowing the device to pick up electric fields in the bulk substrate. So we've got a device image here on the left. Over on the right, I'm showing calculated offset charge that is coupled to the qubit island, which is this little bit in the middle here that's separated from ground plane by a small gap. And so in this plot, we're imagining that we've got a unit charge that's placed somewhere in the bulk substrate. We can calculate the electric fields that are produced by that charge, find where the field lines terminate, and we can calculate for arbitrary location of this charge what the applied offset charge is on the qubit island. So the device is a sensor for electric fields. And because we're outside of the normal transmon regime, we have energy bands that are slightly sensitive to a change in the electric field environment of the device. So over in the lower left, I'm showing these energy bands as a function of the applied offset charge. And we see two different energy bands which correspond to two different quasiparticle parity states on the island. I'll talk more about this later in this presentation, but in all superconducting qubit devices, one finds a high density of broken Cooper pairs, excitations out of the superconducting condensate, which we call quasiparticles, which you can kind of roughly think of as unpaired electrons that can tunnel onto and off of the island, changing the charge parity and giving you a little bit of an energy shift. So that's why we see two energy bands. And it turns out that we can monitor the quasiparticle parity by doing a particular interferometric gate sequence on our device to allow us to measure quasiparticle parity. But the other thing we can do is we can just probe the background charge in the substrate by doing a similar type of Ramsey-based interference experiment that involves exciting the qubit to a superposition state, letting it idle, then projecting into the computational basis and measuring again. If we do this type of sequence as we vary the applied offset charge on the island, which we do by adjusting a little voltage that we apply to this orange electrode over here that's weakly capacitively coupled to our qubit island. And we can monitor these Ramsey oscillations, and the phase of those oscillations is going to tell us about the charge state of the device. So that's the type of experiment that we started to do a couple of years ago. And what we saw is that charge noise in superconducting qubits is really quite strange and incompatible with a vast body of literature on charge noise in single electron devices going back into the 80s or so. Now, the charge noise that we measure is large, and also it's got a frequency dependence that's anomalous. We get a 1 over f squared scaling of charge noise with frequency, as opposed to the 1 over f scaling that's typically seen. And so this is all very weird. And it's not just our group in Madison that saw this very strange behavior of charge noise in these qubit devices, but there had been some other earlier experiments by the group in Delft of DiCarlo and the Deveray group at Yale that saw similar strange behavior. So in the course of trying to understand this physics and why charge noise in superconducting qubits is quite different from what's been seen previously in single electron transistors, we did some experiments where we systematically probed the scale dependence of charge noise. And what we found led us to speculate that the charging events that we're seeing have a large spatial footprint, that there was something going on in the substrate that was releasing a large amount of charge that's going to couple to multiple qubits. And so that got us thinking about the possibility of correlated charge noise in multi-qubit arrays. So a little more than a year or so ago, we designed an experiment that was going to allow us to, explicitly look for spatially correlated charge noise in a multi-qubit circuit. So the chip that I'm going to describe involves 4 qubits, 4 weakly charge sensitive transmon qubits, each coupled to its local readout resonator, each with a local charge gate line. We've got 2 qubits that are relatively close together, 340 microns center to center, another 2 that are 640 microns apart. And then these 2 pairs are on opposite sides of a chip with a separation of about 3 millimeters. So we can go ahead and do this Ramsey interferometric gate sequence that allows us to reconstruct the offset charge on the qubit islands. And we can do this simultaneously on all 4 qubits in this multi-qubit chip. And we can just track offset charge as a function of time. And this is what we find. So I'm showing below some time series for this 4-qubit chip measured simultaneously over the course of about 10 hours, plotting offset charge in units of the fundamental charge on the vertical axis. And what we find is that at a rate of about 1 per 5 or so minutes, we find very large discrete jumps of order fraction of an e, significant fraction of a fundamental charge in all of these devices. I should mention that our qubit-based electrometer is only able to sense charge modulo the fundamental charge 1e. So all of the charge jumps that we're seeing are getting aliased into the interval from minus half an e to plus half an e. So there's some aliasing going on. So we find these large discrete jumps, and this is basically what we'd found before and what Deveray's group and DiCarlo's group had seen. But the new piece here is that now that we're monitoring charge simultaneously on multiple devices, we can see that there's a high degree of correlation in the charge jumps that we measure in neighboring qubits. So I'm showing over on the right a little blow up of these time series for the red and the pink qubit, which are separated by 340 microns, and the dark blue and the light blue separated by 640 microns. So we can take this data set and we can plot this in a different way. We can look at the joint histograms of charge fluctuations in these various devices. And what we find is that for the nearby devices, the charge jumps are very highly correlated. So if we threshold at jumps with absolute value greater than 0.1 e, what we find is that there's uh, about a 50, 55 or so percent probability that a large jump that's seen by one qubit is also seen by its neighbor. And even at 640 microns, we see that there's a very strong degree of correlation in the charge fluctuations measured in these different qubit devices. Whereas if you look across the chip at a separation of about 3 millimeters, the correlation is basically just compatible with random coincidence. Okay, so this is the first important experimental result here. We're saying that the charge fluctuations that we measure in transmon qubit circuits are highly correlated on a length scale exceeding hundreds of microns. Okay, so what's going on here? Well, the picture that we have is that there are high energy particles that are constantly impacting the superconducting qubit chip. And so I'm showing here results of some simulations that were done of a cosmic ray muon that's entering the qubit chip. And as it passes through the chip, it's depositing a very large amount of energy in the qubit substrate of order 100 kiloelectron volts. And that's a huge amount of energy compared to the energy scales that are relevant for qubit operation. Typically, we work with modes that have frequencies in the 5 to 10 gigahertz range that corresponds to an energy of order tens of micro electron volts. So these particle impact events are releasing an energy that's 10 orders of magnitude larger than the characteristic energies of our qubit experiments. So what do these impacts do? Well, in the first instance, these impacts are going to release a large amount of charge in the semiconducting substrate. We get about 1 electron hole pair for every 3 electron volts of energy released. And so these impact events are going to liberate of order 10 to the 4, 10 to the 5 discrete charges. Those charges are going to diffuse in the substrate. And here in this simulation, we're showing electrons in blue and holes in red. And that reconfiguration of charge in the substrate is going to change the offset charge that we measure on the qubits, which again are going to be highly sensitive to electric fields in the bulk because of the large size scale of these devices. Okay, so that's the basic physics. And over the course of the last year, working closely with researchers at Fermilab, Noah Korinsky, and at INFN in Rome, a group led by Laura Cardani, we've done some very detailed modeling that allows us to really pin down the microscopic physics associated with these impact events. So the first piece of this modeling is using a package called GEONT4, which was developed by the high energy community to understand interaction of high energy particles with matter. We have modeled kind of a stripped down version of our qubit cryostat that I show here in this image. So it's not fully anatomically correct, but it's got the vacuum jackets, radiation shields, and stage plates with all of the right materials, aluminum, copper, stainless steel. And what we can do is we can simulate flux of cosmic ray muons using the known angular and energy distribution of those muons at sea level. And we can also simulate the effect of high energy gamma rays due to low level radioactivity that's going to be present in the laboratory. And so with GEON4, we can, work through to these numerical studies that allow us to generate a track for each of these simulated impact events. We've got locations where energies are released in the chip, and ballpark numbers for the muons, we find that we get a energy of order of few hundred keV on average deposited in the chip per impact event. The muons leave these very long, straight tracks. We can also look at the gamma rays, which deposit on average about 100 keV, and the gamma rays leave these sort of smaller, squirrely-looking tracks. And we can simulate, many events in order to then, build up statistics and understand the impact of these events on qubit operation. The next piece of these simulations is to model charge transport in the substrate once we've got energy deposits from the different simulated particle impacts. And so here we're building on decades of work by the dark matter community, collaborations like CDMS, cryogenic dark matter search, that have really developed an extremely detailed picture for how high energy impacts will give rise to mobile charge in silicon single crystals. And so, building on that work, working closely with Noah Korinsky at Fermilab, we can understand how these particle impacts will generate both electrons and holes that will diffuse in the substrate and give rise to this reconfiguration of charge that can be sensed by the qubit. And so these charges will propagate out from the impact event. Electrons and holes are going to propagate a little bit differently because of electron valley physics. We get electrons that propagate kind of anisotropically in the crystal, and those electrons tend to move a little bit farther than the holes. And charge is going to move out until they trap, but with a probability that's set by some characteristic trapping length due to defects in the crystal or until they encounter a surface. So we've done this type of modeling, and we've taken the J-on-4 and charge transport modeling that we've done, and we've fine-tuned the parameters in the model in order to get good agreement with the measured histograms of charge impacts, looking both at the single qubit histograms and the joint histograms. And what we find is that we get excellent agreement between the modeling and our data when we take a characteristic charge trapping length of about 300 microns, which is consistent with what the dark matter community uses when they do modeling for their detectors. And there's a charge production efficiency of about 20%, which is telling us that only 20% of the discrete charges escape this impact event. The rest are going to undergo recombination right in the vicinity of the impact event. But with those parameters, we get really good agreement with our measured data. And based on this modeling and based on our experiments, we can make some statements about the impact rates on the chip of both cosmic ray muons and gamma rays from low-level radioactivity. And what we find is that the impacts are dominated by gamma rays, that the muons contribute only at about the 2 or 3% level. And these gamma impacts are occurring at a rate of about 20 millihertz. And this is pretty consistent with what we infer by separately measuring radioactivity in our lab using a sodium iodide scintillator. There might be about a factor 2 discrepancy that's just suggesting that maybe we've got some dominant source of radioactivity within the qubit cryostat. And this is something that we're going to continue to look at more closely in the coming months to really try to pin down where these gamma rays are coming from. Okay.
Before we move on any further, Robert, I do have a few questions.
Sure.
I think from the previous section. So the first question is, the charges liberated by the muon impacts can induce an offset charge greater than 1e. How does that affect your analysis of the power spectrum?
Yeah, so all of any charge that's greater than half an e is going to get aliased into the interval from minus half an e to plus half an e. And so, our analysis takes into account that aliasing effect.
Okay, cool. And then another question asks, Basically, they were talking about how they found it interesting that the pattern was evolving over time. Is this some state evolving, or is this some type of an environmental change? Have you looked at different times of the day?
Okay. No, we don't see any modulation of the event rate with time of day. And, our model is that these events are due, primarily to low-level radioactivity in the laboratory, and you wouldn't expect that to vary from,
Right.
from hour to hour. Yeah.
Okay, cool. I think we're good to move on.
Okay. Okay. So, this liberation of large number of discrete charges, this is kind of the first, um, damaging effect of these impact events. But ultimately, most of the energy released is going to get transferred into a phonon reservoir. And we know that phonons in the substrate are going they're just going to spread throughout the substrate. And high energy phonons can break apart Cooper pairs, generating quasiparticles that can induce qubit relaxation. And so we set out to separately understand whether these impact events would give rise to correlated relaxation events in our multi-qubit chip. And so the experiment that we do is shown here. What we're doing is we're using one qubit, Q1, which is the dark blue qubit in the upper left. We're using that as a monitor of charge in the substrate. And so we're going to use that qubit as a trigger to tell us whether or not an impact event has occurred. And while we're monitoring Q1, we're going to simultaneously monitor Q2, the light blue, and Q4 on the other side of the chip to see if we measure any enhanced relaxation when these impact events occur. Okay, so with Q1, we're doing the Ramsey experiment that's allowing us to measure charge. Q2 and Q4, we're doing a stripped down inversion recovery sequence where we initialize the qubit in the ground state. We're doing initialization by measurement. Then we invert the qubits with an X gate. And then we're basically doing a single point inversion recovery sequence where we let the qubit idle for 10 microseconds and then measure. Now, in the absence of an enhanced relaxation event, we're going to have a little bit of relaxation due to baseline spontaneous emission. But what we find is that when we trigger on these charge events, we get an enhanced probability for Q2 and Q4 to relax during that event. We get a suppression of qubit T1 that extends across the entire chip. So even though the charge event is sensed by Q1, what we find is that not just Q2, but also Q4, we get a suppression of energy relaxation time way on the other side of the chip, okay? And we can see this in the data over here on the right, which is a probability of measuring our T1 probe qubits in the excited state as a function of time from this trigger event. And right around this charge trigger, we see this clear suppression of qubit energy relaxation. And the chip recovers on a time scale of about 100 microseconds after one of these impact events. Okay, so how can we understand this? Well, as I say, most of the energy in the impact events is going to go into a phonon reservoir. Those phonons are going to go everywhere in the chip. They're very weakly coupled to the environment. They relax by interacting with the superconducting condensate and generating quasiparticles. But those phonons are going to get stuck basically right at the superconducting gap edge, and they're going to reside in this chip for a time that is set by the escape time for these athermal phonons to, leave the chip and enter the enclosure that houses the superconducting qubit chip. So basically, the phonons just go everywhere, and they're going to give rise to quasiparticle poisoning that's going to be correlated across the entire qubit chip. And this is a big problem for error correction because basically what's happening here is we have this impact event, and then every single qubit on that substrate is going to experience a period of time where there's severe suppression of the qubit energy relaxation time. And until the chip recovers, the entire quantum processor is basically completely inoperable. Okay, so this is the absolute worst type of correlated error. because, number one, the probability of a bit flip error is essentially unity. When there's an impact event that's releasing energy that's 100 keV, then is so much energy that you're going to generate a ton of quasiparticles. Every qubit on the chip is going to be seeing these quasiparticles, and the T1 time is suppressed, almost to zero, effectively to zero, uh, and it's going to stay that way until these high energy phonons can escape from the chip. So it's a huge error probability, and the other incredibly damaging thing is that it's affecting every single qubit on that substrate. Okay, so this is a real problem. Now, I don't think this is a fatal problem. We've been thinking about how we can mitigate this damaging correlated phonon-mediated quasiparticle poisoning, and there are a number of approaches. You can play some tricks by engineering the superconducting gap on the chip in order to try to suppress the propagation of pair breaking phonons across the chip. There are other tricks you can play to try to very quickly extract the energy from the phonon reservoir. John Martinez has posted a paper to the archive that describes one approach involving backside normal metallization. You can also think about doing some tricks to just suppress phonon transport in the substrate, maybe involving some silicon micromachining. And so we're thinking about some of those approaches as well. And of course, if we understand exactly where these high energy particles are coming from, maybe there's going to be some dominant source that's very local to the qubit chip. And by selecting radio pure materials, maybe we can address the problem in that way. But in general, this is a big problem. Okay. So just to sum up this first part of the talk, we've done this series of experiments that show that high energy particle impacts on the qubit chip are a real problem. And there's kind of a hierarchy of pain associated with these particle impacts. In the first instance, the worst effect of the impacts is the phonon-mediated quasiparticle poisoning. Very high error probability, and all devices on the substrate are going to be affected. So this is a big problem. Now, recently, earlier this week, the Google Quantum Group posted a paper where they're describing the same physics in a larger qubit array, I think involving 26 qubits. And so as a community, we're going to really need to figure out ways to mitigate these high energy particle impacts in order for quantum error correction to work. And I'm very optimistic that we're going to find appropriate fixes. But this is something that, over the course of the next year or so, I think there's going to need to be a big push to figure out the best approach to mitigate. Now, there are a couple other pieces of this. Now, we came to this problem by thinking about charge noise. And the charge noise, of course, will give correlated phase flip errors. Now, one might say that, okay, the transmon qubit in the full transmon regime is exponentially insensitive to charge noise. But the fact is that even for an EJ to EC ratio of about 50 or so, the correlated phase flip errors due to these charging events associated with particle impacts are not insignificant. And so these correlated charge fluctuations really do, I think, represent a real design constraint. Now, ideally, we would like to be able to implement qubits with larger charging energy, which would mean larger qubit anharmonicity, which would suppress leakage errors. But there's a limit to how far you can go there, because eventually you're going to reach a point where charge noise becomes a problem. And it's not just charge noise on the single qubits that we need to worry about. It's these correlated charge fluctuations that are really going to be the limitation. So this is something that's going to need to be thought about seriously as we try to pursue a global optimization of multi-qubit processors. There are some other errors that could be associated with the particle impacts that I think probably are not going to be so important, but just for the sake of completeness, we've talked about the possibility of bit flip errors due to non-adiabatic charge transition transients in our paper. I don't think that's going to be so important.
Before we move on, a
Yep,
couple more questions for you, Robert, if that's all right.
sure.
So the first question is, and I think this is referring to the paper that you just had on the previous slide. In Google's recent archive posting, they showed that the T1 errors, the time scale was closer to tens of milliseconds. Do you know
Yeah.
why your observations were so different?
Yes. So, I've talked with people at Google, and our understanding is that, we measure this 100 microsecond time scale. Google's time scale is more like a couple tens of milliseconds. And we can understand this just by looking at the way that the chips are thermally anchored. So,
Okay.
bottom line is the devices that we measured were much better thermally anchored than the Google devices.
Okay, cool. And then the other question was from a few slides before. I'm not exactly sure which one, but we had somebody asking if we could reduce the impact of these correlated charge noise errors by using different types of substrates. Maybe this is a better question for the end, actually. If we want to talk about that more towards the end, we
Yeah,
can.
yeah, that's a
Okay.
good question, and I think the answer is yes. So maybe we can come back to this at the end.
Yeah, let's pause on that one and come back to that one at the very end, if that's all right.
Okay. Okay.
All right, let's keep going.
Okay. Okay. So in the remaining 5, 10 minutes or so, I'd like to try to answer the question: are these particle impacts the source of non-equilibrium quasiparticles in superconducting quantum circuits? So for decades, researchers have seen in single charge devices in quantum circuits a very high density of quasiparticles, many orders of magnitude, tens of orders of magnitude uh, larger than what one would expect from BCS theory. And the typical densities are about one quasiparticle per cubic micron. So, we know that these particle impact events are happening. They're releasing a lot of energy. They're generating quasiparticles. Now, could it be that these impact events are the source of the large baseline density of non-equilibrium quasiparticles that all researchers in this field see? Well, the MIT group of Will Oliver recently published a paper suggesting that this could be the case. Now, our thinking is that the event rate is too low. We've got an event rate of 1 per minute or so on a centimeter square chip, and the rate of thermal phonons to escape the chip is too high for these impact events to be the explanation for the baseline high density of non-equilibrium quasiparticles. I mean, these impact events are hugely problematic because they give rise to correlated errors, but I don't think that they're going to explain the baseline high density of quasiparticles that we and others see. So, what could be the source of these quasiparticles? So, there was a very interesting paper a couple of years ago from the theory group at Yale uh, of Glasman by first author Manuel Jose, where they describe a new mechanism for quasi-particle poisoning that involves absorption of a pair-breaking photon at the junction. And so this model was put forth to explain some data by Kyle Cerniak and coworkers in the Devereux group, where they did very careful studies to look at the rates of qubit upward and downward transitions conditioned on a parity change. And that data was not compatible with quasiparticle diffusion across the junction, but it did look consistent with this photon-assisted mechanism. And one of the striking things about this Jose analysis of the Cerniak results is that they find that the best fit of the data is reached when they assume narrowband pair-breaking photons with an energy of 2.8 delta, which for aluminum corresponds to an energy of about 130 or so gigahertz. Now, I mean, I remember reading that paper at the time and thinking, well, this is crazy. Why would there be narrowband 130 gigahertz photons in this superconducting qubit experiment? But in thinking about it some more, I realized that the devices that the Yale group is working with are basically little antennas that are going to resonate in a frequency range of hundreds of gigahertz. So you can think about the Josephson junction as a feed point on an electric dipole antenna, and there's going to be a standing wave resonance that's set by the length of this device, which is going to establish a frequency where the device is going to absorb photons with very high efficiency. And so we can understand the antenna mode of this 3D transmon qubit quite simply by thinking about this simple electric dipole antenna model. But how can we think about other types of qubits, which are typically implemented as metal patches that are embedded in some cavity in a ground plane? Well, it turns out that we can think about these more typical 2D qubit structures as the aperture or slot duals of wire antennas. And so there's a principle in the antenna world called Babinet's principle. It basically involves some symmetries in Maxwell's equations that allow you to map between these sort of aperture or slot structures where you've got an island embedded in a ground plane. You can map from that type of structure to the electromagnetic dual wire structure. And when you look at the impedances of the aperture structure and the wire dual, then they're related in this way, where eta here is the impedance of free space. So with this mapping, we can actually understand how typical superconducting qubit structures are going to resonate and radiate in the hundreds of gigahertz range. So to just move things on a little bit quicker here, being mindful of time. So let's look at a couple typical qubit geometries where you've got a circular island embedded in a continuous ground plane. Well, that, as it turns out, is the aperture dual of a wire loop, which of course is a resonant antenna at a frequency where the wavelength is matched to the circumference of the loop. If you look at this type of structure where you've got rectangular island embedded in a ground plane, then that actually is the aperture dual of a so-called folded dipole antenna, where you've got a total length of this structure that's equal to half a wavelength, and you get a reversal of the polarity of the current at the ends of the dipole, which is going to give you kind of coherent addition of the electric fields across the different arms of the dipole. So even if you look at a complicated structure like the so-called Xmon qubit, you can understand that that Xmon is the aperture dual of kind of this funky folded dipole antenna, where you get a coherent radiation from the horizontal arms of the dipole, and then you got destructive interference on the vertical arms. So bottom line is just almost any qubit that you're going to want to implement using two-dimensional superconducting thin films, it's going to want to resonate and radiate in the hundreds of gigahertz range. So with this knowledge, we can then go ahead and understand how resonant absorption of pair-breaking photons is going to couple to our qubit junction. We can model the junction as a tunnel resistance in parallel with the capacitance. It turns out that we get a good conjugate match to this antenna mode for typical junction parameters. And we can work out for concrete qubit geometries the effective antenna bandwidth of different qubit structures. And what we find is that for more or less any superconducting qubit geometry you might think to implement, you get a bandwidth of order few gigahertz. Even these differential qubit geometries that are pursued by the IBM group, and this particular geometry is taken by the tantalum qubit from Hauck's group, you end up with noise bandwidths of order gigahertz. So using this analysis, we can understand the coupling of pair-breaking blackbody radiation to our qubits. And what we find is that the measured rates of quasiparticle poisoning of order 100 hertz or maybe kilohertz are compatible with absorption of blackbody photons with a blackbody temperature of about 300 millikelvin. So I think what's very likely is that the non-equilibrium quasiparticles that we and other groups measure are due to pair breaking photons, not from a 300 millikelvin black body necessarily, but from higher temperature stages, pair breaking photons that are not completely getting filtered out as they make their way down the qubit leads into our qubit enclosure. And then those pair breaking photons are very strongly coupled to our junction through the resonant antenna modes of our devices. So, and that thinking is published in a paper that we posted to the archive just last month, and um, I'll show the archive citation here at the end. One other little piece of this that I'll just mention briefly is that this kind of Babinets duality analysis can be used to, in a very simple way, understand the ultimate limits to qubit T1 due to radiation at the qubit frequency. In this case, the qubit we can model as an electrically small antenna, and with a few lines of algebra, you can work out the ultimate limits to qubit T1 due to radiation at the qubit frequency. And what we find is that for state-of-the-art qubits, we're approaching these ultimate limits imposed by radiation. Now, we need to do some more sophisticated modeling because it turns out these T1 limits depend quite strongly on the effective permittivity of the substrate. And when you're talking about a wavelength that's large compared to the thickness of the substrate, not so clear at this point what number you want to take for that effective permittivity. So we need to do a little bit more analysis there. But anyway, I think we're getting to the point where we need to think seriously about that limit imposed by radiation. So I think I should wrap up, leave some time for questions. I want to acknowledge the excellent work that has been done by my collaborators to get this all together, especially senior grad student Chris Weiland, who's wrapping up his thesis and will be soon interviewing for positions. I also want to acknowledge the great work that's been done here by junior student Sohair Abdullah, who's contributed a lot to the experiments. The antenna modeling work was spearheaded by an outstanding undergraduate, Owen Rafferty, and I want to acknowledge his contributions especially. Okay, with that, I'll put up this summary slide. If you want to learn more about our work on characterizing correlated errors, you can take a look at this archive paper from last December, and the more recent work on understanding photon-assisted quasiparticle poisoning is described in this paper that we posted on the archive last month. Okay, with that, I'll wrap up. Thank you, and I'll take any questions.
Thanks again so much, Robert. We had a lot of people in the chat saying this was a really, really informative talk, and they say thank you. I promised somebody in the chat we would come back to that one question about the substrates. So maybe we could just ask you to expand a little bit about that, that we sort of left off in the middle there earlier.
Yeah, so I think this is absolutely true. I mean, there's a reason that the dark matter community uses high purity single crystal silicon or single crystal germanium for their detectors that are designed to look for WIMP impacts. It's because we get great transport of charge in these high purity crystals over long length scales. And for qubits, of course, that's going to be problematic because we would like to confine the energy that's released by these impacts to a very small volume so that it doesn't couple to many different qubits. So, one could certainly look at alternative substrates like sapphire, which is, not really exotic. A lot of people in the superconducting qubit community do use sapphire substrates. I think it's quite possible that charge transport in sapphire is going to be very different, and maybe the charging event is going to have a much smaller spatial footprint. But you can also think about more exotic approaches that would involve kind of intentionally dirtying up the substrate to introduce scattering centers. If you can do that in a way that doesn't degrade the dielectric loss tangent of the substrate, then that would be beneficial. And you can also think about similar approaches to suppress the transport of pair breaking phonons. So those ideas all make sense to me.
Yeah, I agree. It makes sense to me too. So this person says, thank you so much for this talk. This T1 analysis is classical. Would you get something similar if you applied quantum formula such as the fluctuation dissipation theorem?
Well, okay, fluctuation dissipation theorem. I mean, fluctuation dissipation theorem is a way to relate, a dissipative dissipation to to noise. I mean, there you're thinking about an equilibrium situation. In our case, we've got these impact events that are really, taking you far outside of equilibrium. And now I'd have to think about this. Not clear to me that it would be useful to try to think along those lines. But the data that we're showing, I mean, it's quite compatible with this picture where we generate a high density of quasiparticles. And over the course of the last 10 years or so, a number of groups have studied the impact of non-equilibrium quasiparticles on relaxation in Josephson devices and also high Q resonators. And the relaxation events that we measure, I mean, they're really kind of compatible with this quasi-particle mediated relaxation picture that has been described previously.
The speaker just wanted to clarify that he was asking in reference to the radiative T1 calculation. I don't know if that would change your answer at all.
I see. Yes. Okay. So there, I mean, yeah. And so, I mean, here we know that T1 can be calculated from the real part of the admittance shunning the junction. And, when you've got this antenna mode, then there's a dissipative part to that antenna impedance. And so, yes, I mean, this is very conventional. We're just saying that any sort of dissipation at the qubit frequency, and of course, if you're connecting the qubit up to this electrically small antenna, then that does represent a dissipation channel. Then that will give you relaxation. So, yes, I mean, this is compatible with that kind of conventional thinking.
Okay, awesome. We really have a ton of questions here, which I think speaks to how important people think this topic is. I have a couple more questions here, which are very speculative, but what the heck, it'll be fun. So this person asks, we're talking about, thin film superconducting devices. Would this translate, in your opinion, to any type of quantum dot-based systems in terms of correlation?
It could. And this is something that we're thinking about. And in fact, we've got a new project at Wisconsin that's supported by LPS and ARO to understand a little bit more deeply these types of correlated errors from particle impacts, not just in superconducting systems, but also in semiconducting quantum dot systems. And so in this larger project, I'm working with Mark Erickson, who's also on the faculty here at UW-Madison, and Shimon Kolkowitz. And so my thinking there is that for quantum dots, the devices are going to be much more sensitive to charge than superconducting qubits. On the other hand, the effective sensing area to electric fields is going to be much, much smaller. So this could be a problem. Might turn out that for practical quantum dot devices that are being pursued for computing, maybe it'll turn out that the sensing area is so small that the correlated errors are a non-issue. But at a minimum, it's something that we need to study experimentally to understand whether this is going to be a problem. And so at Wisconsin, we do have some follow-on work that is aimed to directly answer that question.
Okay, awesome. I think I have one more question for you here, which is sort of my question as well. But in your opinion, when we're talking about mitigating these impacts caused, would we be able to better impact? Sorry, would be able to better mitigate these impacts by using different types of shielding and doing experiments underground, like in some of the dark matter experiments? Is it worth it? Basically, should we be painting, the cryostat on the inside black? What should we be doing, I guess, in the near term to sort of combat these errors?
Right. Well, so there are a couple of different pieces here. So there's the particle impacts, and so one way you could try to address this problem is kind of a brute force approach. We just go underground. That's certainly a way to eliminate any cosmic ray muons. Now, if you go to an underground lab, of course, you're still going to have to deal with the problem of low-level radioactivity in the lab. But there are special facilities where researchers have gone to great lengths to create a radio pure environment that's going to be compatible with very sensitive searches for certain types of dark matter. And so this is worth looking at. And, in fact, my group, in collaboration with researchers at Fermilab, we do have some plans in the near term to do qubit experiments in an underground laboratory facility with really extensive shielding. Um, now, I don't know necessarily that type of brute force approach is going to be the way forward. It seems kind of cumbersome. Maybe if you have, one 100 million qubit array in a massive dilution refrigerator, then maybe the cost of operating it underground is kind of just a incremental add-on to the cost of constructing and operating the system. But it seems kind of clunky. I think other approaches that involve mitigating at the chip level are going to be kind of a much more promising path forward. And I'm very optimistic that as a community, we're going to find an appropriate workaround. I mean, now that we understand the physics, I think it's clear what we're going to need to do, how to engineer the devices to really contain the energy released by these impact events to a very small volume where you're not getting these correlated errors. And there's also straightforward steps we can take to really extract the energy quickly so that it doesn't damage the processor. Now, there's a separate question about painting things black. And that sort of approach has been taken by the IBM group and others using special IR absorbing coatings to suppress the flux of pair breaking photons. And that sort of thing is definitely useful. My group, others, IBM, Google, they've all seen improvements in performance and suppressions of quasiparticle poisoning rate by playing those sorts of tricks. So I think that's definitely useful, and that's going to relate to the second piece of this talk on the resonant absorption of pair breaking photons. I'm also optimistic that by really kind of understanding and engineering this antenna mode, we'll be able to develop devices that are much more robust against photon assisted quasiparticle poisoning.
Yeah, I totally agree with you. I'm optimistic as well. So I lied. I actually have one more question for you, and then we'll let you go because this is, I think, an interesting point. So this person says, "Great talk. Thank you so much. Do you have an opinion as to the relative importance of the quasiparticle poisoning versus the two-level systems, which are causing some energy relaxation as well?"
Yes, that's a great question. And, the fact is that these are both difficult problems. And I think these both are limiting the performance of current state of the art qubit devices. And they're pushing you in opposite directions. So we know that these two-level systems reside in lossy dielectrics at interfaces. Could be the lossy interface between the metal and the substrate, or it could be the native oxide of the superconducting metal. And because this is an interface effect, the the obvious workaround is to increase the scale of the device. But as you go to larger and larger devices, then the device is going to want to radiate more. And the radiation, you can have this radiation at the qubit frequency that's ultimately going to limit energy relaxation time. But you've also got this resonant radiation mode that will promote the coupling of quasiparticles to the qubit. And that's a problem. So there's a tension between this the need to protect against loss due to resonant TLS and the need to suppress this photon-assisted quasi-particle poisoning or to suppress radiation. And you know these are both problems, and one needs to pursue a global optimization of the system, and it's a complicated business. Now, I think probably in the short term, the quasi-particle piece of this, I think, isn't limiting energy relaxation times of qubits currently, but I think it's very possible that this photon-assisted uh, quasi-particle poisoning does account for the relatively high levels of spurious one-state occupation that we and other groups see. I mean, typically you've got qubit initialization errors of order 1% to a few percent. I think it's quite possible that it's absorption of these resonant pair-breaking photons that's kicking the qubit up to the excited state. And so that's an issue as you go to larger systems and you really want to maintain extremely high fidelities to do error correction. But the dielectric loss, I think, is very severe. As you try to go to larger qubit arrays, you're basically ending up with these dead spots in the qubit spectrum where high fidelity operation is just impossible. So I think probably in the short term, the TLS is more important. But at the end of the day, as a community, we're going to need to figure out a global optimization of these superconducting qubit arrays, and it's complicated. It is absolutely complicated.
I think that's accurate and a good note to end on. It's definitely complicated, going to take a lot of creative solutions, but Robert, I want to thank you again so much for your really great talk. We had so many questions and a lot of really active participants. So thank you so much for joining us here today.
Well, thank you. It's been fun.
All right,
It's
great.
been fun.
We'll be back here next week, everybody. We hope you tune in for the next seminar series on Friday at noon. And we wish you a great rest of your day. Thank you so much for tuning in.